Here's problem 11-12. The skater extends her arms horizontally, holding 5 kilogram mass in each hand. She is rotating about a vertical axis with an angular velocity of 1 revolution per second. If she drops her hands to her sides, what will be the final angular velocity in revolutions per second if her moment of inertia remains approximately constant at 5 kilogram meters squared and the distance of the masses from the axis changes from 1 meter to 0.1 meters? Alright, so we're going to deal with angular velocity in revolutions per second. We normally change it to radians per second, but since we're using the same units for initial and final, we'll be fine. Let's model the skater as some kind of moment of inertia associated with the body, and then she's holding out these two masses at arm's length. So her initial moment of inertia is going to equal the moment of inertia of her body plus the moment of inertia of each of these point masses. Now they're located a distance r initial away in both directions, and they are point masses. So acting as point masses, they each have a moment of inertia of mr squared. So we're going to have a 2 mr squared initial for this situation, which is going to be equal to 5 plus 2 times the mass, which is 5 kilograms. And initially, she's holding it 1 meter away. Square that. So it's going to be 5 plus 10, or 15 kilogram meter squared. That's our initial moment of inertia. In the final analysis, she's holding these closer to her body now, and the radius is going to be much smaller. So we have our R final here for the radius. Masses are still the same, but the moment of inertia is going to be a lot less. So our final moment of inertia is again going to be equal to the moment of inertia of the body plus 2m r final squared for the point masses. So this is going to be 5 plus 2 times the mass, 5, but our final radius is 0.1 meters squared. So this final moment of inertia is going to be 5.1 kilogram meters squared. Well, since the torque is radial, there's going to be no net torque on the system, and hence angular momentum will be conserved. So we'll have that the initial angular momentum will equal the final angular momentum, and that means that the initial moment of inertia times the initial angular velocity will equal the final moment of inertia times the final angular velocity. Solving this for the final angular velocity, we have that is equal to the initial moment of inertia divided by the final moment of inertia times the initial angular velocity. And that would be equal to 15 divided by 5.1. Our initial angular velocity in revolutions per second was 1 revolution per second. And our units of the moment of inertia will be canceling out, so we're going to end up with units of revolutions per second, giving us 2.94 revolutions per second. So really, when she pulls it close to her body, that portion of the moment of inertia is going to be so small, 0.1, that it's almost negligible, and we almost have a ratio of 3 to 1 here. So it's approximately 3 revolutions per second. But it's conservation of angular momentum, and it's why she speeds up when she pulls these masses inward to her body.